So, welcome to the, I don't know which lecture of probability and statistics. And today we will continue with statistics, and topic in statistics is estimating parameters. Meaning the parameters of random variables which model our data. So, as I told you last time, we have in fact two types of estimates. The first one is the point estimate. And the second one is interval estimate, or more often we call it confidence interval. I will write only CI. And what does it mean? It means that when we have a set of data, we construct the model. Let's say we draw the histogram and we decide that the data come from normal distribution or from exponential distribution or some other distribution. And the distribution depends on one or more parameters. And we want to estimate these parameters. We want to estimate a concrete number of these parameters, which is the first type of estimates. But we are aware of the fact that we have our random sample, and the concrete realizations of this random sample, it means the concrete data set, can differ when we repeat it again and again. And so, for example, when we estimate the mean, which is the parameter lambda in Poisson distribution, the parameter mu in normal distribution, and so on, it is estimated as the average, as the sample mean applied to the data, which corresponds to the classical average. And when we have one data set, we can have the average equal to 10. When we have another data set, the average can be equal to 10.5. In the third sample, the average can be equal to 8.9, and so on. And so in different samples, we have different point estimates. Therefore, we want to construct also the interval where the parameter, the real parameter, lies with some given probability. It is the confidence interval. We will start with point estimate. The definition of the point estimate is maybe a little bit confusing for you because it is defined as, in fact, an arbitrary function of the random sample, which gives us a concrete number when we applied this function to the concrete data, to the concrete realization. And when we applied it to the random sample, so it means to the random vector, we obtain, in fact, a random variable. And then the nice estimate is such that the expected value of this random variable is equal to the real parameter. If you don't understand this definition, and if you don't understand me, what I said, it's normal, it's natural, because it is really, really difficult to imagine it. So let's say in such a case, consider the example where we wait for a bus. We know this example very well. So we wait for a bus. We do not know the schedule, or better say, we know neither schedule nor the time interval between bus arrivals. We have a random sample, x1, and so on till xn, where xi is the time awaiting for the bus during the ith journey. So we have a sample of n waiting times for the bus where we don't know the time interval, and it is the task, it is our aim to estimate the time interval between bus arrivals. So, what do we know? We know that this x1, x2, xn, and so on are the time of waiting for the bus during the ith journey. So we denote x the waiting time for the bus. Not during the first journey, during the fifth journey, the waiting time, because it is still the same. We come to the bus stop and we are waiting for the bus. So x is the waiting time for the bus, and we know that x has uniform distribution where the lower boundary is known, it is 0, because it is the shortest time we can wait. But we don't know the upper boundary. And the upper boundary is, in fact, the time interval we want to estimate. So, we want to estimate B, and when we have an estimate, we write the letter which corresponds to the parameter we estimate, and we write this hat. This hat means that the thing we estimated is only the estimate from the data. We have many possibilities because, in general, the point estimate is an arbitrary function on the random sample. But of course, because we want the parameter to be unbiased, so it means that in expected value it will be equal to the real parameter, we must a little bit think about the way how we estimate it. So we know that for the uniformly distributed random variable x, the expected value is b minus a over 2, which is b over 2 in our case. So it means that b is equal to 2 times the expected value. And it leads to the idea that the estimate of b can be 2 times the estimate of the expected value. And the expected value is estimated as the average. So in general, in theory, 2 times the sample mean. Or we can think about the time of waiting. We have many, many times of waiting. So maybe the maximal time can be good estimate of the upper boundary. Or we can make some other ideas. So there are many, many possibilities how we can think about the estimate. And when we make this estimate, we want to verify whether it is unbiased. So now I will show you how to verify whether the estimate is unbiased or not. So in the first case, we want to calculate the expected value of such an estimate, which is given by twice the sample mean. We know from the last time that the sample mean is calculated as 1 over n times the sum from 1 to n from xi. This is constant, so it can go in front of the expected value. And we have the expected value of the sum of the random variables xi, which is nothing than 2 over n times the sum of the expected value of xi. And we now, you can see here, that the expected value is equal to b over 2. So we get 2 over n times b over 2. And because we have the sum of these numbers which don't depend on I. So we have 2 here, we have n here, and we obtain b, which means that we verified that the expected value of such an estimate is equal to the real estimate. Now, what about b? The expected value of b, of the second example, expected value of the b estimate is equal to the expected value of the maximum of x1. How did I write it? Okay, maximum of xi over all I. Let's denote this random variable as y. And because maximum of random variables is again a random variable. let's start with the distribution function, cumulative distribution function is denoted as, let's say, f. So f in variable x is equal to the probability that y is less or equal to x, which is equal to the probability that the maximum of xi is less or equal to x, which means that all the random variables in the sample must be less or equal to x. And since we know that in the random sample the random variables are independent, we can write that it is the probability that x1 is less or equal to x times the probability that x2 is less or equal to x times the probability and so on that xn is less or equal to x. And all these random variables are in fact the times of waiting for the bus. So it is equal to the probability that x is less or equal to small x powered by n. And this is nothing than the cumulative distribution function of x, which is known. It is 0 for x less or equal to the lower boundary, so it means then 0 in our case. It is equal to 1 for x greater or equal to b, and it is equal to x minus 0 over b minus 0. And so this is the distribution function for x, and we must to power it by n. So when x is from the interval 0 and b, the distribution function is x over b, so it means that the nth power is x over b powered by n. Great, so we have the distribution function. Now we calculate the density. We denote the density as the small f, and the density is nothing than, I will write it just shortly without any conditions, as the derivative of distribution function. And because we know that the distribution function is the integral from the density, so therefore the density must be the derivative of the distribution function. So it is, in our case, n or 1 over b powered by n times n times x powered by n minus 1. And because we can write it as x powered by n over b powered by n. This is, of course, for x from the interval from 0 to b, and it is equal to 0 for x out of this interval, and because out of this interval we it is the derivative of 0 or 1 respectively, So the derivative of constant and the derivative of constant is equal to 0. And when we have the density, we can calculate the expected value of y, which is in fact the expected value of the maximum, which is what we want. So the expected value of y is the integral from minus infinity to plus infinity x times the density x dx, which is in our case the integral from 0 to b, because it is 0 otherwise, x times 1 over b powered by n times x powered by n minus 1, which is dx, which is equal to n over b powered by n times the integral from x powered by n dx, which is n over b powered by n times x powered by n plus 1 over n plus 1 from 0 to b, which is n over b powered by n times b powered by n plus 1 over n plus 1, which is n over n plus 1 times b. Yeah? And it is the problem, because we wanted to have the expected value of the estimate to be equal to b, but it is equal to n over n plus 1 times b. So it means that it is a little bit smaller than the real parameter b. And what now? The heuristical imagination of this situation is such that we have the interval from 0 to b, and we can imagine our n observations, which are uniformly distributed in this interval, like n equidistant intervals, where in each interval we have one observation. So, as I said, it is not the real situation, it is a heuristical explanation of the situation. So in each interval we have one observation, and therefore we can see that when we suppose heuristically that the observations sit in the middle of this interval, we can see that the maximal observation is really a little bit below this b. Because we have n intervals, but it means that we have n plus 1 boundary points. And that's it. It means that when n is very, very large, we are very close to b. But why should we have the estimate which is only close to b, when we can have the estimate of the parameter b whose expected value is equal exactly to b? How can we do it? We can do it so that we take n plus 1 over n times the maximum of xi. Yeah? And when we consider such an estimate, what do we obtain? The expected value of p is the expected value of n plus 1 over n times the maximum of xi, which is n plus 1 over n times the expected value of the maximum of xi. And we know that this expected value is equal to n over n plus 1 times b. So this expected value is equal to n plus 1 over n times n over n plus 1 times the expected value of b, which is equal to b, or expected value of b. The whole expected value is equal to n over n plus 1 times b, so it is the real b. So we can see that now the expected value is equal to b. And so this estimate is again unbiased, while the second estimate was not unbiased, so we say that it is biased. So that's the way how to calculate the expected value. It can be easier, as in the first case. It can be more difficult, as in the second case, but it can be done. And this is the way how we can do it. Okay, and now you maybe think that it is quite difficult to verify whether the expected value is of the estimate is equal to the real parameter or not, that it is difficult to find the estimate of the parameter because we have no rules in this estimate, so don't be afraid of it. There are some methods which give you directly the approach how you can find the parameters. So the first method which I will show you is a so-called moment method. And the moment method works as you can see on the slide. We suppose that the distribution from which the random sample comes is depending on some k parameters. And so it can depend only on one parameter, for example, the parameter lambda in Poisson distribution or exponential distribution. It can depend, or it can have two parameters, like binomial distribution, which has the parameters n and p, normal distribution having the parameters mu and sigma square. And there can be more difficult distributions depending on 3, 4, or sometimes more parameters in practice. And so in general, we suppose that we have k parameters in the distribution. And theoretically, we can calculate, in the most cases, the kth moments. The kth moment, or here I wrote the ith moment, is the expected value of x powered by I. And we can estimate this ith moment from the data as 1 over n times the sum of the observations powered by I. And then we have the estimate of the ith moment from the data, and we have the theoretical estimate depending on these k parameters, or at least some of them. We obtain the system of k equations with k variables. So we only solve this the system of equations, and that's it. The advantage is that it is very simple. Moreover, when we have only two parameters, we can use the second central moment, which is in fact variance in our case, instead of the second moment of the random variable, because usually the variance is known at least in our basic distributions. And so we can work not only with the moment of the random variable, but also with this central moment. Everything what is called moment, in fact, can be used here. And then it is very fast, very simple. What is the disadvantage? I write to here that one of the disadvantage is that the estimate has large variance. Okay, the larger disadvantage is that sometimes it is not possible to calculate the expected value of some moment, of the third or fourth moment, or sometimes it is impossible to integrate the density. Yeah? It can be very difficult to calculate the theoretical ith moment. So therefore, we use this method only for some simple distributions. I will show you an example. A test is written in 5 rooms. There are n students in each of this room. And the only information we have is the number of successful students in each room. So the number of successful students in the first room is 17, 15 in the second room, 21 in the third room, 19 in the fourth room, and let's say 13 in the third room. Estimate using the moment method. The probability of success in the test and the number of students in the rooms. So again, we start with some model. So we denote X, the number of successful students in a room. The number of successful students in a room is, in fact, the number of successes in n trials, because in each room we have n students, each student is a trial. So X is the number of successes from n trials, and it means that it has binomial distribution with the parameters n and p. And this n and p are to be estimated. We know that the expected value of x is theoretically equal to n times p. The variance of x is equal to n times p times 1 minus p. That's what we know from binomial distribution. And we can estimate the expected value as, now I should write the small x, as the average of our values. So the average is 1/5 times the sum of our observed values. The sum should be 85/5 is equal to 17. And it means that the first equation we will solve is n times p is equal to 17. The variance can be estimated as the realization of sample variance, where the sample variance is equal to 1 over, now if you remember, if not you should look to the last video, but I will recall you that in the denominator we have n minus 1, so it is 5 minus 1 in our case. It is from the reason that this this sample variance is unbiased. It means that its expected value should be equal to the real variance. So 1/5 minus 1 from 17 minus 17, it is x1 minus x square plus 15 minus 17 square, which is x2 minus x plus, and so on, plus 13 minus 17 square, and it is equal to 1/4 times 17 minus 17 square, I'm sorry, I forgot the square before, 0 plus 15 minus 17 is minus 2, powered by 2 is 4, plus 21 minus 17 is 4, square is 16, plus 19 minus 17 is 2, square is equal to 4, plus 13 minus 17 is equal to minus 4, square 16. So it is 20 plus 20, it is 40, 1/4 times 40 is equal to 10. So it means that the second equation we will solve is n times p times 1 minus p is equal to 10. And that's it. We have two equations with two variables, and we solve this system. So when we divide the second equation by the first equation, because we suppose that neither n nor p are equal to 0, we obtain that 1 minus p is equal to 10/17, which means that, I'll write it here, that p is equal to 1 minus 10/17, which is 7/17. And that's the estimate of the success, of the probability of success in the test for each student, because we don't know the students, so we suppose that the probability is the same for all the students. And for example, from the first equation, we get n times 7 over 17 is equal to 17, which means that n is equal to 17 times 17 over 7, and it should be equal approximately 41.3. But n is the number of students in each room. So of course, in practice, we need n to be integer. So n can be estimated as 41, or maybe you want to round it, the number up, because of some reason, because you need to calculate how many tests you should prepare or for next time, and so on. So it's up to you whether you choose this, or in some special cases, from some economical reasons, when you need to prepare the number of tests for the next time, you should round it up. It depends on the situation. Yeah? So for us, it is important how to estimate these parameters by the moment method. And as I said, this method has some disadvantages. One of them is that it cannot be calculated in all cases. So now I will show you another method, which is very well known and very often used, and it is maximum likelihood method. So the maximum likelihood method, or I will write only MLE, like the maximum likelihood estimate, is based on the following idea. We suppose that the realization, so it means the concrete values which we collected, of the random sample x1, x2, and so on till xn is the most probable situation. And so we suppose that the values which we sampled are the most probable we could obtain. And what does it mean from mathematical point of view? It means that the probability that the first value is equal to x1, the second one is equal to x2, and so on, and the last one is equal to xn, is maximal possible. This probability is in fact equal to the product of the marginal probabilities and again we have a model. Of these random variables, So it means that X has the same distribution as x1, x2, and so on till xn. So it is equal to the probability that x is equal to x1 times the probability that x is equal to x2 times the probability and so on that that x is equal to xn. And so we can write that it is the product from I equal to 1 to n of the probabilities that x is equal to xi. And because we have the model for x, for example, x comes from x has the Poisson distribution, then we know this description. In this description, we know the value which we usually denoted as k, and we don't know the parameters. I will show you an example. So it means that this is the function which depends on the parameter. I will denote it in theta. It is a classical notation for the parameter in general. And of course, theta can be more dimensional. So theta can be the vector of 2 or 3 or more parameters. So in general, theta is the notation for 1 or more parameters. L is the function which is called the likelihood function, and this is the function which should be maximized. And because we suppose that this probability is maximal possible. And so we will look for such a parameter which caused that this function is maximal possible. How do we look for the maximum? It is looking for the extreme. So we need to calculate the derivation, set the derivation to be equal to 0, and solve this equation. But L is quite a crazy product. So instead of calculate the derivative of the product, we would like to calculate the derivative of sum. And it is possible because when we take an arbitrary logarithm with the base greater than 0, for example, the natural logarithm, of the function, we can maximize this function instead of the likelihood function. Because where is the maximum for the function capital L? There must be the maximum of its logarithm. So instead of this function, we very often maximize this log likelihood function. And then it is very easy. We calculate the derivative, set the derivative equal to 0, and solve this equation. In the case that the parameter theta is more dimensional, we calculate the derivative due to each parameter. So we have partial derivative, and that's it. Yeah? So this is what is written in the following slide, and what I show you how it's done. Yeah? First, we construct so-called likelihood function, which is this product. I explained you why. And then we follow the classical approach for finding the extreme of the function. As I said, here we calculate the partial derivative, especially in the case when we have, or especially in the case when we have more parameters, we can have more equations, and all these equations, or all these functions, all these derivatives must be set to be equal to 0 in order to get the system of equations. But we will usually use it only for one parameter, so it is the classical derivative. This is the maximum likelihood, and as you noticed, I used the parameters, I used the probability that x1, x2, and so on are equal to some concrete values. So I use the descriptions or the way of calculations for discrete random variables. But when we have the continuous random variables, the probability that x is equal to some value k is replaced by the density, and the approach is the same. So it means that, as you can see in the slide, the likelihood function is constructed as the product of densities instead of these probabilities. And the log likelihood function is in fact, it is the logarithm of this density. Yeah, so the only difference is in fact here when we construct the likelihood function, that it is the product of the densities instead of the concrete probabilities. Okay, so I promised you an example of this function, of this method, I'm sorry. So, the example of using maximum likelihood method can be the following. A company sells cars. The numbers of cars sold per week were the following. In the last 10 weeks. It is a small company, let's say only one part of the company, one shop, where they observed that they sold 2 cars, no car, 3 cars, 2 cars, 5, 2, 3, 0, 2, and 2. Let's say in order it is easier. The aim is construct a model for the number of cars sold per 1 week, and using the maximum likelihood estimate method, or maximum likelihood method, depends on you. Estimate its parameter. So, construct a model means nothing than to set which distribution the number of cars sold per week comes. So X is the number of cars sold per week. And since the number of cars sold per week is the number of events which are independent to each other, then it means that it is a typical case of random number with Poisson distribution. The Poisson distribution is given by one parameter lambda, and the description for the probability that X is equal to K is lambda powered by K over K factorial times E powered by minus lambda for K to be equal to 0, 1, 2, and so on till infinity, because the number of the events is theoretically unbounded. The events are independent, so there is no reason for the boundary. Okay, so lambda is the parameter which is to be estimated. Following the steps in the discrete case of maximum likelihood, we know that first, in the first step, we should construct the likelihood function. In our case, the parameter is called lambda, so I will call it lambda here. And it is the product of these probabilities where k are the observed values. Yeah, so now we are in the opposite situation as than we were in the theory. Now we know k, and we don't know lambda. We want to estimate it. So it means that we have lambda powered by the first value over the first value factorial times e powered by lambda times lambda powered by 0 over 0 factorial times e powered by lambda times lambda powered by 3 over 3 factorial times e powered by lambda times and so on times the last value is 2, so lambda powered by 2 over 2 factorial times e powered by minus lambda. So let's make it simpler. 10 times we have the member e powered by minus lambda. So it means that we have e powered by minus 10 lambda times lambda powered by 2 times lambda powered by 0 times and so on. We know that 1, 2, 3, 5 observations are equal to 2. So we have a lambda powered by 2 5 times in the product. Then we have lambda powered by 0 twice in the sample. Lambda powered by 3 is twice in the sample, and lambda powered by 5 is once in the sample. And in the denominator, we have some factorials, but we know that we will look for the extreme. We will calculate the derivative. So, in fact, we can write that it is a constant. It is something which doesn't depend on lambda. Okay. So it is e powered by minus 10 lambda times lambda powered by 10, 0, 16, 21, lambda powered by 21 over this constant. Now we should calculate the derivative from this term. It is quite easy to calculate derivative immediately, directly. But I will show you the second step. It is quite easy and it makes it simpler a little bit. So we will calculate the logarithm. I will choose the natural logarithm because I have e in this likelihood function. So the logarithm of L lambda, which is the logarithm of e powered by minus 10 lambda plus the logarithm of lambda powered by 21 minus the logarithm of the constant, which is minus 10 lambda times the logarithm of e, which is equal to 1, plus 21 times the logarithm of lambda minus logarithm of a constant. So it is another constant. Let's denote it constant 2 when this was constant 1. Yeah? And in the third step, we calculate the derivative of this function, which is minus 10 times lambda derivative is minus 10 plus 21 times the derivative of the natural logarithm of lambda is 1 over lambda, and the derivative of a constant is equal to 0. So let's say minus 0. So it is 21 over lambda minus 10, and it is equal to 0. So it means that the estimate of lambda is equal to 21 over 10 or 2.1 if you want. We should verify that it is maximum and not the minimum, but believe me that it is constructed so that this solution is always, at least in the statistics, is always equal to the maximum. So we won't verify whether it is maximum. In our cases, it will always be the maximum. So this is the result of the maximum likelihood method. And as you can see, it is maybe difficult to understand all these theoretical things around it, but when you use the calculation with this maximum likelihood method, it is very fast, very easy, and it is more general, or it has more general usage than the previous method. So it was the topic of point estimate of the parameters, and now we go to the interval estimates or to the confidence intervals for the parameters. So what does it mean that something is confidence interval? Theoretically, it is again the function constructed from the random sample, but it's natural because everything in statistics must be in fact the function of the random sample, because that's the only thing which we have in our hands. So when we have a random sample, then the function on this random sample is the confidence interval when it satisfies the following. First, we set the probability, which is the probability for the real parameter to be in the given interval. And then we this probability is equal to 1 minus alpha, because alpha is in fact some error. Yeah? it is a very, very small probability that the parameter lies outside this interval, even when our random sample was as it was. And then let's say the couple of functions, when we have a concrete realization, the concrete values, it will be the couple of concrete values, satisfying that the real parameter lies between these two numbers is equal to 1 minus alpha. We can construct also the lower interval, which is one number, where this number is less alpha with the given probability, and the upper interval. But here we will calculate, in the most cases, we will calculate only the so-called two-sided confidence interval. So it means we will construct two numbers, which are the boundaries for the parameters, where the parameter lie between these two boundaries with probability 1 minus alpha. I will skip these. These intervals. Yeah, we'll solve them later, and I will show you one quite universal, quite general approach how to construct the confidence interval for the expected value. Why? Because the expected value is very often connected to the parameter whose confidence interval we are looking for. And for example, in Poisson distribution, the parameter lambda corresponds directly to the expected value. In exponential distribution, the expected value is 1 over the parameter lambda. So when we have the confidence interval for the expected value, we can construct the interval for the parameter as well, and so on and so on. Yeah? So we are looking for the confidence interval for the expected value of x, where x is the model. Right? It means the random variable from which the data comes from. And we will use central limit theorem. The central limit theorem says that the random variable set n, which is the sum of many random variables which are independent and identically distributed, minus n times the expected value of each of them, so for example x1, over the variance of n times the variance minus the square root of the variance of the sum, which is n times the variance of each of these random variables, goes to a random variable set with standard normal distribution. Its quantiles, which are denoted U, where each quantile has an index P, can be found in statistical tables. One of these tables you have on my webpage. You can Google it, you will find it everywhere. And I just recall what the quantile mean. So when we have a normal distribution, the quantile u beta means that it is such a number on the horizontal x that the area below the curve of the density is equal to beta. And as I showed you last time, when we are looking for the boundaries where the area between these two boundaries is 1 minus alpha, and we suppose that the interval is symmetric, then we have the quantile with the index 0.975 on the right side and the quantile with the index 0.025 on the left side. Why? Because when we want to have 1 minus alpha inside, it means that the area alpha half, I'm sorry, I work with alpha equal to 5% because it is the most often used number, but in general it is lambda half here and 1 minus lambda half here, because lambda half of the area must be the area of this tail. Alpha half must be the area of the right tail, and when alpha half is the area of the right tail, it means that 1 minus alpha half must be the area from this boundary to the left. Therefore, we used these two indices. Okay, so what does it mean? It means that the probability that Zn lies between u alpha half and u1 minus alpha half is equal approximately, but we suppose that n is large enough, so we can say that it is equal to 1 minus alpha. Okay, it means that the probability that the sum of xi minus n times the expected value of x1, which is in fact the number, the parameter we are looking for its confidence interval over n times the n times the variance of x1, and it is less or equal to u1 minus alpha half. Now we can divide everything by n. So of course only the numerator was divided by n. And now what can we do? We can multiply everything by this square root of n, all three sides. Here we have the sample mean, and here we have the variance of x1, which can be estimated as the sample variance. So we will replace the theoretical variance by the sample variance, because for large n they are close enough. We will denote this sum over n as a sample mean, and we will multiply everything by this square root of n. So it means that the probability that u alpha half over the square root of n is less or equal to the sample mean minus the expected value of x1 over the square root of sample variance, which is less or equal to u1 minus alpha half over the square root of n. And now we will multiply everything by the square root of Sn square, which is in fact the sample standard deviation, and the square root of square. So the probability of u alpha half times Sn over square root of n is less or equal to xn minus expected value of x1, and it is less or equal to u1 minus alpha half times Sn over n. Now we subtract the sample mean. And finally, we multiply everything by -1. So it means that instead of less or equal, we will write greater and equal. So the probability that xn minus u alpha half times Sn over square root of n is greater than equal than expected value of x1. And this is greater or equal to xn minus u1 minus alpha half times Sn over square root of n. And moreover, you can see that these quantiles are symmetric. So it means that here we have some positive number, and here we have the negative number with the same absolute value. So it is in fact minus the positive number on the right side. So instead of minus u alpha half, we can write plus 1 minus alpha half. And it means that the confidence interval, which is usually denoted as 1 minus alpha times 100% confidence interval, is the sample mean plus minus u1 minus alpha half times the sample deviation over the square root of n. Yeah? And it makes sense because when we are looking for the confidence interval of expected value, it must be found somewhere around the sample mean, because the sample mean is the estimate of the expected value. Yeah? So of course it is the sample mean plus minus something. And then the interval is as wider as larger the variance of the data is. It makes sense, and because we have when we have wild data, of course that the interval must be wider than for the data which are close to the expected value. It is as shorter, more as narrower as the number of the data, because when we have more data, of course that the interval is narrow, and when we have less data, it must be wider because there are more possibilities for the expected value to be farther from the sample mean. And this quantile only correct the probability for being inside the interval. And so this quantile only say how large the tail is. Yeah? And this is the way how to find the general confidence interval for the expected value. First note, this interval is only so-called asymptotic. It means that it's not exact, and it is more precise when n is larger. Yeah, so it is more and more precise with growing n, but when we have n large enough, we can be satisfied with this estimate. The second note is that sometimes it can be difficult to calculate the sample variance, so it means its square root sample deviation. So for some special cases, we can replace this sample deviation by some function of the mean. For example, for Bernoulli distribution, or alternative distribution, we know that the expected value is equal to p, and the variance is equal to p times 1 minus p. So it means that when we subtract the expected value by the mean, we can approximate the sample variance by such a formula. For Poisson distribution, we know that the expected value, which is equal to lambda, is equal to the variance. So we can replace the sample variance by the sample mean in the case of Poisson distribution. Yeah? And then it led to some easier form without this sample variance in some cases. But in general, when we are not in the situation of some simple random, in some simple distribution, we can use in general the confidence interval given by the general description. Random, the sample mean plus minus the quantile with the index 1 minus alpha half times the sample standard deviation over the square root of n. That's it. So the topic of the parameter estimate is over. I thank you for your attention.